Hello friends, in this lecture we continue our discussion on quantum free electrons and Sommerfeld theory. Let us try to understand the difference of CV in case of quantum and classical electron gas. What we have discussed previously is that the higher energy of quantum free electron gas is because of the Pauli's exclusion principle. We need to fill a large number of states, which is of the order of 10 power 23, but we can put only 2 electrons per energy level. As a result, the electrons occupied the topmost energy levels. Their energies are very high. Now, let us convince ourselves that the lower CV of quantum free electron gas is also due to Pauli's exclusion principle. Now, let us let us assume that these are the energy levels that we need to fill, and let us try to do it at t equal to 0 and t greater than 0. So at t equal to 0, we just put 2 electrons per energy level. And let us assume that this is the Fermi energy. Right, all the states above the Fermi energy, they are empty. Now let us go to some higher temperature. Then let's see that how do we fill the states at some temperature which is greater than 0. So this was already there, right? So this was already there in case of t greater than 0. And now what happens is that I have put 1 electron in the excited state. Note that I cannot put, say, this electron which is lying at the bottom, correct? I cannot excite it to the next energy level because the next energy level is already full. Okay, so that means only the electrons which is close to the Fermi energy, only they can be excited, not all the electrons. So electrons close to the ground state energy, they cannot be excited because there are no empty states available to put them. So less energetic electrons cannot be excited to the next energy level because the next level already has 2 electrons and cannot accommodate 1 more. As a result of this, only electrons within kBt below the Fermi energy, they can be excited. For example, if you look at this figure, we cannot excite electrons from this region, right? We can only excite electrons from some region which is close to the Fermi energy, and they will be excited to these levels. Okay. If we consider the plot of energy versus this density of states times Fermi function, we have already seen this plot before, correct? The number of electrons given is given by the area under the curve. Thus, number of such excited electrons is approximately the area under the shaded region. So, if you look at this shaded region, right, this is where this plot differs from the ground state curve, right? And everywhere else you see, right, in most of the regions, the ground state and excited state curve, they just coincide with each other, and only in this region they are different. They are different, correct? So that means if we can find out the number of electrons within this shaded region, right, which has an energy width of kBt, the width of the energy is kBt, then we know that how many electrons are getting excited, correct? And then how can we find? We can just approximate it, right? We know the density of states at the Fermi level. The Fermi level is here. We can just excite, we can just find the area under the shaded region, correct? By calculating the area of this thing, correct? And then that is given by kBt times G of F. Now, note that, so this is the number of electrons getting excited at some finite temperature. Now, what is the amount of excess energy that these electrons are having? Since the energy at some temperature, we can just write it as kBT. So this is the amount of excess energy that these many electrons are having, okay, at finite temperature. So that means if we want to calculate the excess energy or the energy density above the ground state energy, then what we can then this is just the number of electrons, right? So this is the number of electrons which has been excited, and this is the excess energy that those number of electrons are having. So if we just multiply these two, we get a term like kBT squared times G of F. Now you can compare this number to the exact result, and you see that they differ by this factor only, okay? So the exact result has this factor pi square by 6, which is some number which is of the order of 1. So that means if we so our this qualitative argument that we have presented here is really good, because if we just match with the exact result, they are of the same order of magnitude. Now let us try to compare with experiments. Do we observe the linear T dependence of CV as predicted theoretically? Now, if you take a solid, then there are other sources contributing to CV. For example, the atomic vibrations. And at room temperature, the atomic vibration will dominate. For example, this is how so for example, if you look at the red curve, this is how the CV for the atomic vibration changes as a function of temperature, right? So you see that, so this is approximately, this is the room temperature. And you see that at room temperature, the CV, because of this atomic vibration, they are dominating. But as you go to lower temperature, what happens is that this CV, this falls off as a function of T cube, right? This falls off as T cube as you go to some temperature which is below room temperature. And now you see this blue curve. For this is the CV for the free electron gas, and you see that this has a linear temperature dependence. So as the temperature drops down, this also decreases, but this decreases linearly. Since the vibrational part, right, the atomic vibrational part, since it decreases or since it falls off as T cube, then at very low temperatures, what will happen is that the electronic part will become dominant. And this happens only at maybe like a few Kelvin, okay? So now what we do is that let us just add the two parts, right? So the total CV, correct? The CV. So we have the electronic part, which has a linear temperature dependence. And then we have the atomic vibration part, and at low temperature, it has a like cubic temperature dependence, right? So now if we we can just rewrite this equation, correct? We can just write like CV by T. This is equal to gamma plus A T square, right? So this is what is written here. And then let us look at some experimental plot. So this plot is shown for potassium. And if you plot C by T as a function of T square, then this is what you get, right? So this is the equation, correct? And then you see that it will intersect this axis at some point, correct? And in the experimental plot, so where it intersects, correct? So that is the, let us call it as gamma observed, okay? So in fact, this gamma observed, right, the intercept at T equal to 0, that is the experimentally observed value of the free electron specific heat, okay, or free electron heat capacity. Now, this implies that if we do the experiment and you look at the temperature range where it has been plotted, so this is like 0.1 Kelvin square, right? So this is like really low temperature. So if we can experimentally measure this and plot this, then from the experimental observation, we can find out the free electron heat capacity. Now, from our theory, we know that the free electron heat capacity is given by pi square by 2 T by Tf and n times kb. Okay, so what we do is that in place of n, we just take 1 mole. Okay, so Z is the number of valence electrons per atom, and we multiply it with Na, the Avogadro number, right? And then the entire term we can write it in this form: pi square by 2 T by Tf. Z is the number of valence electrons, and R is this constant, and R is equals to n times the Avogadro number times the Boltzmann constant. Thus, for free electron gas, we can define gamma as gamma F is equals to this, right? So now what we are going to do is that we are going to compare gamma naught and gamma O, that is the gamma observed from the experiment, and gamma F, this is the theoretical prediction. Let us compare gamma F and gamma O, the theoretical and experimental value. Now, we know that EF is equals to, we can convert it to some temperature scale, kb Tf, which is equals to h cross square kf square by 2m. This implies that Tf is proportional to 1 over m, and if you look at the form of gamma F, yeah, then gamma F is inversely proportional to Tf. So that means we can write that gamma is proportional to the mass of the electron. Now we define this term, okay, MO by MF, right, which is just the ratio of the observed value of gamma and the theoretical value of gamma, and ideally this should be equal to 1, correct? So now let us see how does the number look like if we compare gamma observed and gamma free electron. So you look at this table, and then you see that these numbers, right, they are not exactly equal to 1, but the order of magnitude is matching. Thus, the metals shown in this table, they are reasonably well described by quantum free electron gas model. Let us now talk about the electrical conductivity of quantum free electrons. We are going to use Newton's second law of motion. We shall justify the use of classical approach later. Instead of P, we are going to use the eigenvalue of the momentum operator. So this is the form of second law of motion. So this is like dP dt, and what we are going to use is, you know that the momentum operator, this is the eigenvalue h bar k, and we are going to use that in this equation. That means h bar dk dt is equals to the force. Rest of the equation remains as before, right? So this force in this case is given by the Lorentz force. Now let us consider only electric field such that the magnetic field is 0. Then what we have to solve is h bar dk dt. The force is minus E charge of the electrons times E the electric field, and then we just rewrite this as dk is equals to minus E by h bar dt, and then we can write the solution as k of t minus k of 0 is equals to minus E t by h bar. So this is what is written here. Assume that E is equals to 0. So in that case, so if I take E equal to 0 here, in that case, what will happen is K of T is equals to K of 0. If we draw a Fermi sphere in the K space, the Fermi sphere will be centered at the origin. So you look at this diagram. So when E is equals to 0, then the Fermi sphere, we know that this is the ground state of the free electrons. And in case of E equal to 0, the Fermi sphere will be centered at the origin of the K space. This is equivalent to the statement that if you do not apply any field, you do not get any current. Note that if the Fermi surface is centered at the origin, sum of all the K vectors inside the sphere is equals to 0. That is because we have like 4 quadrants, 1, 2, 3, 4. And then if you just sum over all the K points within the sphere because of the spherical symmetry. In this case, this is like a circular symmetry because we are showing it in 2D. So because of the circular symmetry, the sum of the K vectors inside the Fermi sphere will be equal to 0. And that implies that net momentum is equals to 0. That is, when the E is equals to 0, then the Fermi sphere will be centered at the origin. The moment Fermi sphere shifts from the center of the K space, the net momentum will be non-zero. So if you look at this diagram now, right, the Fermi sphere has shifted from the center of the Fermi sphere has shifted from the origin. And now if you just sum over all the K points, right, it will not give you 0, but there will be some net momentum along this Kx. And we know that the net momentum implies that there is some net current. Thus, for E not equal to 0, in this case, the center of the Fermi sphere has shifted from this point, from the origin to this point, correct? And that is given by delta K is equals to minus EET divided by H bar. Now, the question is, does the Fermi sphere keep shifting forever? Because if you look at this equation, then you see that as time is increasing, the center will keep shifting from the origin. Does it happen in that way? The answer is no, because if that happens, that will imply the momentum will increase forever with time as we apply the electric field. But we know that it does not happen in that way. Similar to the Drude model, we have to assume some scattering, and that scattering will keep the displaced Fermi sphere in a steady state. So you see, this is the Fermi sphere will reach some steady state, right, where the center is not at the origin, but then it will not keep shifting forever. Okay, it will remain there, and that is because of the scattering. Similar to the Drude model, we introduce the relaxation time tau, correct? So in this equation, we just replace T with tau. T will be replaced with tau, correct? And we can now find out the velocity at the steady state. So what we do is H bar K is the momentum. So if we divide that with mass, then that will be the velocity, right? And then this is the velocity when we reach the steady state, and remember that the steady state is reached because of scattering. And now we have the steady state velocity, and then we can write that J is equals to minus NEV, and in place of V, if we replace this, then J is equals to N E square tau by M electric field, and then we know that this term is the electrical conductivity, sigma is equals to N square tau by M. Now let us try to justify the use of a classical equation for transport in a quantum model. Note that the momentum of the highest occupied energy levels, that is given by H cross times Kf, right? So thus we can just take this as the value of momentum uncertainty. Okay, so this is the value of momentum uncertainty. And now we can, using the Heisenberg uncertainty principle, we can find out the position uncertainty, and that will turn out to be del x is h bar by delta p. Where delta p, if we just put this value, then we see that this number turns out to be 1 by kf. Remember that kf is of the order of 1 angstrom inverse, right? So that means 1 by kf, the position uncertainty, that will be of the order of 1 angstrom. Okay, now this implies that the classical description is not possible if the electron is localized within some region which is of the order of 1 angstrom. Okay, in that case, we have to actually use the quantum description. But let us understand the length scales related to conduction electrons. Okay, the mean free path at room temperature, that is of the order of 100 angstrom, which is much greater than this 1 angstrom. And the electric field or temperature gradient which we apply, right, that is of the order of like 1000 angstrom. That is like maybe like 1 volt per 1000 angstrom and so, or like it can be even higher. So that means the length scale that we are talking about in for this transport problem, that is much higher than 1 angstrom. Okay, thus we can actually use the classical equations to understand the electronic transport. Now let us just see that what properties are going to change if we use like quantum theory, and what properties are not going to change. Okay, let us try to understand that. Note that all the properties related to the velocity or energy are going to change. So this is what we have seen, right? The velocity of the quantum electron gas is much higher. And also the energy of the quantum electron gas is much higher because we are using the Fermi-Dirac statistics and we are not using the classical Maxwell-Boltzmann statistics. For example, we have seen that the CV is going to change. And then we didn't discuss this, what is thermopower, but then thermopower is something that depends on CV, so that will change. The mean free path, right? So this is like Fermi velocity times tau, correct? So since this is a function of velocity, this will also change, and so on. And now let us see that what are the properties which are not going to change. Whatever is not related to velocity or energy is not going to change. For example, the electrical conductivity sigma, right, which is like n e square tau by m, right? It is not a function of velocity or energy, so it is not going to change. And if we do the Hall coefficient, that will also not change. And of course, the relaxation time is not going to change, and so on, right? Not going to change in the sense that if we take the, for example, these properties, right, they do not depend whether we are going to use the classical model or quantum model. And these properties, they will depend on whether we are going to use the classical model or quantum model. Now, there is only one exception, correct? And it is the thermal conductivity. Kappa is equals to 1/3 CV V square tau, right? You see that it depends on the heat capacity, right? And it also depends on the velocity. So you may expect that, yes, kappa should depend on whether we are going to use like quantum model or classical model. But you see that this in quantum model, right, the CV is the actual CV is 1 by 100 of the classical model, right? And in quantum model, so that means the actual CV, that is like 1 by 100, correct? So that is the difference between classical and quantum. And if you look at the velocity, right, velocity in quantum model is 10 times. So we have a term v square. So that means this will be the actual value of v, right? The quantum value of v, that is like 100 times more. And then you see that this factor of 100, they will cancel out each other. And then as a result, although kappa depends on CV and velocity, the value of kappa, it will not matter whether we are using the classical or quantum model, because the errors that we are making, they are getting cancelled out. And that is what led to the remarkable success of the Drude model to predict the Weismann-Franz law correctly. Finally, let me conclude by listing out the differences and similarities between the quantum and classical electron gas. So if we calculate the velocity, then we see that the quantum free electron gas, they have 10 times the velocity than the classical free electron gas. And then the mean free path, since this is a function of velocity, naturally this is also 10 times higher in case of a quantum model. The energy of the quantum free electron gas, that is 100 times more than the classical model, right? So I have compared the energy at 300 Kelvin, that turns out to be 37.5 MeV, whereas even at 0 Kelvin, the energy of the quantum free electron gas is of the order of 1000 millielectron. Okay. Now, if we calculate the heat capacity, then the quantum model, the heat capacity is 1/100th of the classical model. And then there is something called thermopower, which is a function of heat capacity, and naturally that is also 1/100th in the quantum model, right? And note that if you, for example, this thermopower, you can actually experimentally measure, and the experimentally measured value is actually matching with the quantum model. And even for CV, you can measure it experimentally, and that also matches very well with the quantum model. So that means quantum theory is actually able to solve certain anomalies that we observed in classical theory. Now, the next term is the thermal conductivity. And thermal conductivity in case of quantum and classical model, they are same. But this happens because the error in calculating the factor of CV and error in calculating the factor V square, they cancel out, and that is why kappa is same in the classical and quantum model. Electrical conductivity is sigma. They are also same in the classical and quantum model because it does not depend on either velocity or the energy. And as a result, if we calculate the ratio of kappa divided by sigma t, they are surprisingly, right? They are like very close to each other in case of quantum as well as classical model. And keep in mind that this is because the error that we made in the classical model, error in calculating CV and error in calculating V square, they are cancelling out each other. Okay. And then the Hall coefficient, they are also same in case of quantum and classical model. Thus, what we found is that the quantum model managed to correct these numbers, right? Correct the value of heat capacity. Now we have a value which is matching very well with the experimental values. It managed to correct the value of the thermopower. It is also now matching very well with the experimental value. But then the anomaly that we observed for the Hall coefficient, right? The sign anomaly, right? That we cannot just correct by using the quantum free electron model. So we still have the the sign anomaly that we of the Hall coefficient that we found for certain metals in the Hall coefficient that persists, and this implies that the free electron model is not capable of explaining this sign anomaly of the Hall coefficient. Correct. Thus, we need to go beyond free electron model and take into account the electron-ion interaction. Thank you.